Hi students, this is a third video on molecular polarity. Today we're going to talk about how to identify molecules' polarity based on the shape of the molecule, the bond type of the bonds within the molecule, and we're going to use a simulation in order to do that. I'm going to go ahead and walk through what you would see in your notes, which are going to be found in the left-hand column. So the first thing to note that if there's only one bond in the molecule, the bond type and the polarity will be the same. So if I have an H to H bond, I have a bond type that is polar, but if I look at the entire, it's a non-polar bond. And if I look at the entire molecule, well, because the entire molecule is only two atoms, it's going to be a non-polar molecule type overall. If the molecule consists of more than two atoms, we must consider the shape. And to do this, you have to draw out a Lewis dot structure, or you can use the PhET simulations that we've included in your Schoology folders. So, to determine its polarity, if we have lone pairs on the central atom, we're going to have a polar molecule. So my example here is if we have H2O, what would have been a linear molecule has been bent because of the lone pairs. And if I look at CO2, there are no lone pairs on the center atom, so it remains a straight and symmetrical molecule. So we have to also look at the spatial arrangement of atoms. If the bonds cancel each other out and there is symmetry, then we're going to have a nonpolar molecule because the dipoles actually cancel each other out. If all the bonds cancel each other out, we're going to have a nonpolar molecule overall. So I'm going to go ahead and hop on over to the simulation. We're going to look at some of this. So if I have a compound that has just two atoms in it, it doesn't matter what I have, it's going to be a linear molecule, so my molecular geometry is linear. Depends on what these two atoms are. If I have a hydrogen with a hydrogen, then it's going to be a nonpolar molecule, but if I have a hydrogen with something that is a polar bond, then it makes the molecule polar. So I want to go through some of the shapes that are polar and some of the shapes that are non-polar. So when we have a linear molecule that has a lone pair on it, that's going to be a bent shape, and that's going to be a polar molecule because we lose symmetry. If I have two lone pairs on it, well, it stays bent, and so we still have a polar molecule here. Okay, let's add a bond. This is a trigonal planar shape, and if all the outer atoms are the same, or they are nonpolar, then we are going to have a nonpolar molecule. But as soon as I throw a lone pair on it, it takes that triangle and bends it into a pyramid. So now we have a polar molecule. If I add one more, we have a tetrahedral. And again, if this is perfectly symmetrical, then we have a non-polar molecule. But as soon as I were to mess with something and throw a lone pair on it, it would throw off the polarity. But that's not one of the shapes we talked about. Okay, now I'm going to pop on over here, look at some real molecules. Let's look at HF. If I have two different atoms and I look at their electronegativities, hydrogen's 2.1, fluorine is 4.0, so I have a difference of 1.9, which means there's going to be a dipole. The dipole is pointed towards fluorine because it's more electronegative. Now, if I'm looking at the molecular dipole, the whole molecule, it's going to have a dipole pointed in this direction. So this is a polar molecule. Let's go to oxygen. Double bonded. Can't see the lone pairs out here. If I have two of the same elements, we're going to have a difference of 0. And so you'll see that there is no dipole here. which means that this is a completely nonpolar molecule. And if I look at the electrostatic potential, you'll see the sharing of electrons is even, whereas with HF, you'll see that the sharing of electrons is unequal. Okay, let's move on down. Let's look at CO2. CO2, I've got two different elements. The difference in electronegativity is 1, which means it's a polar covalent bond type. So if I look at the bond dipoles, that means oxygen's ripping electrons away from carbon on both sides. But because there's perfect symmetry and the dipoles are actually going to cancel each other out, you'll see that there is no molecular dipole, so the molecule is nonpolar. And the sharing of electrons is going to be even. It's symmetrical. We're going to look at a couple more and we'll finish this out. Let's look at water. The electronegativity difference means it's polar covalent bonds here and here. I have dipoles, both pointing towards the oxygen because it's more electronegative. If I look at the overall dipole, we have a directional shape that goes straight up. The sharing of electrons is unequal. So this is a polar molecule with polar bonds. Let's look at CH4. We have a tetrahedral shape. All of the outer atoms are hydrogens. We have a nonpolar bond type, so all of these bonds are nonpolar. You'll see that there are dipoles. Of course, we classify this as nonpolar. Kind of an interesting shape. But if we look at the molecular dipole, there isn't one. So this is a nonpolar molecule. The sharing of electrons is equal because it has perfect symmetry. Now, what if we change one of those hydrogens to something with a fluorine? Well, you can see a couple of things. Fluorine is very electronegative. It's going to rip electrons away. So the bond dipoles are pulling the carbon in the center, except for carbon is being pulled away by the fluorine. But you'll notice that now I have an overall molecule dipole because of fluorine. The sharing of electrons is unequal, which means we have a polar molecule.